The next exercise actually is number 8 that we want to do, but that depends on exercise 7. So let's first see 7. In this one, we have a positive integer n which has been written in terms of powers of some prime p, like this. N is a polynomial expression in p where the coefficients, these ai's, are integers which are non-negative and less than p. Just like you can express any positive integer in your decimal representation where the base is 10, you can view this expression as representing n in a number system where the base is p and where the digits are these ai's. There are p available digits here from 0 all the way up to p minus 1, just like there are 10 digits available in the decimal system starting from 0 ending at 9, like that. But anyway, that's not the point here. The point is that n has been expressed like this. Now, the exercise asks you to show that then the exponent of the highest power of p that will appear in the prime factorization of n factorial, not of n, okay, n factorial. For this number, if you find the prime factorization, there will be a largest power of p that will appear, and the exponent of that power is this, n minus the sum of the coefficients there divided by p minus 1. I will of course not solve this, it's left to you, but now we are going to use this to see what we can do with exercise 8. Exercise 8 has two parts. This is part A, where we have to use exercise 7 to show that the exponent of the highest power of some prime p that divides p to the power k minus 1 factorial. That means there we had n factorial here, and here in place of n we have p to the power k minus 1, and that largest exponent is this, p to the power k minus p minus 1 times k minus 1 divided by p minus 1. And this is the solution to part A. We first use this identity that we know from algebra. We can express p to the power k minus 1 as this product, p minus 1 times p to the power k minus 1 plus p to the power k minus 2 and so on until you reach 1. This is something you know from classical algebra. And then what we do, what we normally don't do with this product is that we don't again multiply, okay, because this is something that we use for factorization, factoring this thing. But then if we multiply all the terms of this sum by p minus 1, then we get a polynomial expression in p, where all the coefficients now are equal to p minus 1. Are we allowed to have p minus 1 as those ai's? Yes, because p minus 1 is not just non-negative, actually it's positive because p is a prime. So the smallest value of p is 2. But at the same time this is also less than p. So that means we have expressed this n, which is p to the power k minus 1, as a polynomial expression in p. That means as a sum of powers of p multiplied by these p minus 1s. And that is why we can now apply exercise 7 result directly here, and that tells us that the exponent of the highest power of p which divides this factorial would be this, namely that n, which in our case is p to the power k minus 1, minus from which we subtract the sum of all the exponents, all of which are p minus 1. But now the question is, how many p minus 1s do we have here? If you start counting, for this first power of p you get 1, for the second power of p you get another 1. So like that, if you start counting from here up to this term, there are k minus 1 number of p minus 1 plus 1 extra. That means there are k p minus 1s. That is why we have this middle term, and you can just write these two things separately. And of course the denominator is b minus 1. Now you go back and see what you had to prove. This is what you wanted. So that's the solution to part A. And next we have 8b, where we have to determine the highest power of 3 that divides 80 factorial and also the highest power of 7 that divides 2400 factorial. So we just straight away apply part A. By part A, the highest power of 3 dividing 80 factorial, and we also note that 80 is 3 to the power 4 minus 1, is this. Keep in mind highest power, okay, not just the exponent. So we need to write 3 to the power that thing that we found in part A, which in this case is 3 to the power 4 minus, I am talking about the exponent only, 3 to the power 4 minus 4. This 4 is actually that k, okay, and p here is 3 times 3 minus 1 divided by 3 minus 1, and this is 36. So this just means that if one expands 80 factorial, this itself would also be very large, and then factorizes that number. This will be the power of 3 that will appear there. That's the largest power of 3 that will appear in the factorization. Similarly, the highest power of 7 dividing this other factorial, which also has this form, 7 to the power 4 minus 1 factorial, is this power of 7, where the exponent again is just like that, 7 to the power 4 minus 4 times 7 minus 1 divided by 7 minus 1, which equals 396. So this is the power of 7 that will appear in the prime factorization of this gigantic number, whatever it is.